All right, welcome back to Miss Leslie's videos, everybody. I'm trying to be happy right now, but this is my third take. It's my third take of this video, so I'm not having that good of a night tonight. It is roughly 8:22 p.m. All right, so I am about over making these videos. So I apologize. If I make a mistake, I don't even care at this point. It's just gonna happen because I'm not doing this for a fourth take. So let's do this. Today we are going to do factoring polynomials. So you guys learned how to do factoring. Previously we've talked about some techniques, but all of those dealt with quadratics. And in this unit we are really not focusing on quadratics. We're focusing on higher degree polynomials. So our factoring is going to be dealing with those higher degree polynomials. All right, so there are three kind of new types of factoring that I'm going to show you today. All right, so I'm just kind of zooming my page in really quick before we jump over to it. Now we are going to jump over to it. Here we go. All right, so factoring higher degree polynomials. So like I said, there are three new types of factoring. Let me just squish this a little bit more because you can't really see. There you go. So we have something that's really similar to quadratic factoring. So I've just called it quadratic factoring with parentheses because we're not actually factoring quadratics. But it does use this similar technique, that box method, to do factoring. All right, then we have something called factoring by grouping, and this is literally what it sounds like. You're going to factor by grouping pieces of your polynomial together and by pulling out a greatest common factor. All right, and then the last type of factoring is factoring perfect cubes. So factoring perfect cubes is kind of similar to when we talked about factoring like difference of squares, because it does only happen when you have certain situations that are met, but instead of perfect squares, these are going to be perfect cubes. All right, so we're going to do one example that goes with each one of these types of factoring problems. All right, so let's just start with the quadratic because we're not factoring quadratics. That's too easy. But it's the quadratic type factoring. Let's start with that one first. All right, so let's just zoom up in there. Why not get all up in the nitty gritties? Okay, so when I say this is like quadratic factoring, it's because it is going to use that standard box method that we've been using to do our quadratic factoring. All right, now this type of factoring, even though, like I said, you guys have just done it with quadratics, it works with a lot of different situations, but it does have to kind of fit the quadratic type setup. What I mean by that is when you factor a quadratic, you have like ax squared, right, ax squared plus bx plus c. Well, there's what the I don't even know how that happened. I don't even know what I touched on the keyboard that did that to me, but whatever. Okay, we're just moving on because I'm not doing another take, guys. All right, so there's like this pattern right here. All right, so when you factor a quadratic, your first exponent is a 2. It's always going to be an even number. The second exponent we have is a 1, and you probably never thought anything of it because you just thought it went like kind of in order. But the significance of the 1 is that it's half of the highest exponent, which is a 2. All right, and that's an important thing. So using that box method actually works for any polynomial that fits into this category. You have an even exponent for your largest exponent, then your middle exponent is half of that big one, and then you have a constant, which is just a number at the end. So the pattern is ax to some even power plus bx to that even power divided by 2 plus some constant. All right, and if you have that set up, you can just use your standard box method to do factoring for that polynomial. So for example, if I had ax to the 6th plus bx cubed, right, because it's half, plus c, I could use the box method. All right, so like I said, this is just your standard box method factoring. All right, and it's gonna work anytime you have this pattern. So you have the highest exponent that's an even number, your next exponent is exactly half of that even number, and then you have plus or minus some constant at the end. All right, and then if that is our setup, then we can just use this box method that we use for quadratics. So let's just do the example that goes with this factoring technique. So that's our first one right here. So number one, y equals x to the fourth plus 6x squared minus 7. So take a look at those exponents, right? We have 4, which is even. Our next exponent is exactly half, so 2, and then we finish with that constant of 7. So this pattern tells me that I can use just a standard box method type of factoring to go with it. Now the instructions for this problem, I know I'm kind of zoomed in, but it says that it wants us to put the following polynomials into factored form and then determine their zeros. All right, so I have two things I have to do. So I have to get it fully factored, and then I have to find the zeros. All right, so I'm doing both of those things as I answer this problem. Okay, so I'm just going to go ahead and set up my box. Now, just like with quadratics, I'm going to put my leading coefficient, my first term, in that top left corner. So this is going to be an x to the fourth. All right, and again, just like normal quadratics, I'm gonna put my constant in the bottom right-hand corner of my box, so minus 7. Now, to figure out what goes in the diagonal boxes, again, just like quadratics, I'm gonna do a times c, so it has to multiply to a times c, and it has to add to b. All right, so in this problem, we just have a leading coefficient of 1. So a times c is going to end up being just negative 7. And my b value is going to be 6. So I want two numbers that multiply to negative 7 and add to 6. Take a second, think about it. I hope you got it. It's positive 7 and negative 1. All right, so they multiply to negative 7 and they add to positive 6. So in my boxes, that's what I'm going to put. I'm going to put those two magic numbers, 7 and negative 1. Now, because my b term is x squared, I'm going to do 7x squared and negative x squared. All right, so you do have to put the x squared piece instead of just the x piece because that's our exponent. All right, so 7x squared and then negative x squared. Remember, these two diagonal boxes should add up to equal whatever the b term is. All right, so that means our variables have to have the right exponents. Boop, boop, boo, doo, doo. Okay, so again, just like normal factoring, I'm going to go ahead and pull a GCF out of that top row. So x to the fourth and 7x squared, they have x squared in common. So I'm going to pull out an x squared. And now I'm going to do like reverse multiplying. So x squared times x squared gives me x to the fourth. And x squared times 7 gives me 7x squared. Now I go down, x squared times negative 1 will give me negative x squared. And to double check, negative 1 times 7 does equal negative 7. So guess what? I factored correctly. So I now have y equals x squared plus 7 times x squared minus 1. All right, now I need to make sure I read my directions carefully because this does say put the following polynomials into factored form. It means like the most factored form. So I want to check and make sure that none of these two factors can go any further. Well, x squared plus 7 is definitely as far as it can go. I can't do anything else to that x squared plus 7. It is what it is. But x squared minus 1 can be factored because it's the difference of perfect squares. 1's a perfect squared, x squared is a perfect square, so I can use the difference of squares to factor that x squared plus or x squared minus 1 even further. And yes, you do have to do that. So I have y equals x squared plus 7. All right, and then I set up my two parentheses. One gets a plus, one gets a minus, and I square root each term. So x squared square rooted is just x, and 1 square rooted is just 1. All right, so this now, I guarantee you, is fully factored. So here is fully factored y equals. Now the next piece that my instructions say to do is to find all of my zeros, which means I'm going to take each one of my factors and set them equal to 0 and solve for x. So I have x squared plus 7 equals 0, x plus 1 equals 0, and x minus 1 equals 0. All right, this is going to give me x squared equals negative 7. I have to square root both sides. Remember, if you take a square root, you must also put a plus or minus. So that's going to give me x equals plus or minus the square root of negative 7. So I'm not going to leave the negative under the square root. Remember, if you have a negative under a square root, it can come out as an I. So I have plus or minus I root 7. That is that 0. This one is going to give me x equals negative 1, and then this one gives me x equals positive 1. So there are my zeros. Now, a quick trick to make sure you have everything. Remember, the degree of your polynomial is telling you how many zeros that your function has. So my degree for this polynomial is 4. So I want to make sure that I have 4 intercepts in my answer. All right, so the first one, plus or minus I root 7. Well, that counts as 2. Because it's plus and minus. So that's 2 zeros. This is 1, and then this is 1. That is a total of 4. So I have all of my zeros. I'm good. All right. Hopefully that felt okay. That was our first new type of factoring. We're going to move on to our second type of factoring, which is my personal favorite out of all 3 of these, which is factor by grouping. All right, so factor by grouping is literally exactly what it sounds like. Now, the one thing you have to have to do factor by grouping is you need 4 terms. So you need a quanomial, quartomial? I don't know what 4 terms is. Something omial that sounds like 4 at the beginning. I don't know. All right, you need 4 terms. My husband is, I'm sure, just heard me say that. I'm super embarrassed that I don't know what it's called. Nothing important, honey. It's fine. Don't worry about it. I'm making a video. I'm not talking to myself. I'm not crazy. Anyways. This is my third take. I'm not doing another one. It's okay if I'm weird. You guys will deal with it. It's fine. You guys should know by now. Okay, anyways, factor by grouping. We need 4 terms, all right? So something like this, like ax cubed plus bx squared plus cx plus d. That's 4 terms. Uno, dos, tres, cuatro. There we go. There's some numbers in there. All right, so factor by grouping literally means you group your different parts. So we're gonna group the first 2 terms, we're going to group the second 2 terms, and then we're going to pull out a greatest common factor from each. All right, now, once we pull out a greatest common factor, we're going to end up with another greatest common factor, which sounds kind of funky, but we're just going to do an example because it doesn't make sense when I just talk about it. All right, so basically the technique is you group the first 2 terms, you group the second 2 terms, you pull out whatever GCF each of those little pieces has in common, and then you should be able to find another greatest common factor after you've done your first greatest common factor. And that's where the fun part comes in, kind of. All right, so let's just do this so you guys can see what I'm talking about. All right, so number 2 is a factor by grouping type of problem. So you have 4 terms, 1, 2, 3, 4. All right, so what we're gonna do is we're gonna group the first 2. Let's do that color. Group the first 2, group the second 2. Yes, we're going to keep the negative with the 12. All right, it goes with it. And now what we're going to do is we're going to pull out a common factor from each one of those groupings. So looking at my first grouping, I asked myself, okay, what do they have in common? So I have 4x cubed minus x squared. All they have in common is an x squared. So I can pull that out. All right, so I'm going to pull out x squared. That leaves me with 4x minus 1. Perfect. All right, now I go to my second parentheses, my second grouping, and I see, okay, what can I pull out of this one? Now, I always want to pull a negative out if it's in front of that first number because I don't like the first number in my parentheses to be negative. So I'm going to pull out a negative, and I also can pull out 3. So I'm going to pull out a negative 3. That's going to leave me with positive 4x minus 1. Now, do you guys see the second greatest common factor that I can pull out? Look at this. Each one of my parts now has a 4x minus 1. Remember, this is now a term, this is a term, 2 terms, all right? Each of those terms has a 4x minus 1, so I can pull out the 4x minus 1, and then I'm left over with an x squared and a minus 3. That's factor by grouping. All right, now before I kind of call it quits, I want to make sure I can't factor anything else further. So 4x minus 1, that cannot be factored anymore. That's a linear thing going on now, and they don't have a greatest common factor, so it's good. Moving on to the second parentheses, x squared minus 3. Now, if that 3 was, say, a 9, then I would be able to do difference of squares, but it's not. It's just a 3, so guess what? That is now fully factored. All right, the last piece is to figure out the zeros. So I'm going to take each one of my parentheses, equal it to 0, and solve for x. So 4x minus 1 equals 0, and x squared minus 3 equals 0. This is going to give me 1/4. This is x squared equals 3, square root each piece. Make sure I put my plus or minus. My head is in the way. Make sure I put the plus or minus in front of the square root of 3, and that is just x equals plus or minus the square root of 3. Again, we want to make sure that we have all the amount of zeros we're supposed to have. So I look at the degree of my polynomial. It was a degree of 3, which means I should have 3 zeros total. This is 1, and then plus or minus root 3, that is 2. 1 plus 2 is 3. We have all of our zeros. We're good. We are done with that problem. Okay, next, our last type of factoring, I'm just going to move my head. I don't know why. I don't know why I think you guys care about looking at my head, but I just have it. I don't know. So maybe you can know that I'm a real person, I guess. I'm not sure. Anyways, that's off topic. Factoring perfect cubes. Okay, so perfect cubes are exactly what they sound like. So this is first off going to be a binomial. All right, it only works if it's a binomial, meaning you can only have 2 terms. All right, so it needs to be a binomial, and the numbers that you have must be perfect cubes, meaning you can take the cube root of the numbers and you get a whole number. So a lot of times, you guys are pretty familiar with perfect squares. Perfect cubes you might not be as familiar with, but so like numbers, you have 8 is a perfect cube, 27 is a perfect cube, 64 is a perfect cube, 125 is a perfect cube, so on and so forth. All right, so you might have to check to see if something is a perfect cube. You might not know off the top of your head looking at a number if it's going to be. Remember, if you need to check, you can always do it to the power of 1/3. So if you have a number and you're not sure if it's a perfect cube, put it into your calculator and then raise it to the power of 1/3. And if it comes out as a whole number, that means it's a perfect cube. If it gives you a decimal, it means it's not a perfect cube. Okay, so here is the kind of formula for factoring perfect cubes. It looks like this. So if you have a cubed plus b cubed, all right, this is going to factor like so. A plus b, all right, in the first parentheses, and then in the second parentheses, it's going to be a squared minus a times b plus b squared. All right. You can also do this with a minus sign between your 2 perfect cubes. So if you had a cubed minus b cubed, this would be in the first parentheses a minus b. In the second parentheses, it would be a squared plus a times b plus b squared. All right, so the only difference between these 2 formulas, if you're looking at it, right, is this piece right here. All right, so for your second sign, it's always going to be the opposite of what it was in the original one. And there's actually like an acronym, like, you know, you guys get what acronyms are, that can help you remember how to do that second parentheses. And it's SOMPS. Not that anyone really remembers SOMPs, but it is like a word that can help you remember what to do to get that second parentheses. All right, and it stands for the first S, square. So to get your second parentheses, you're going to square to get that first part. O stands for opposite sign. All right, so that sign right there is going to be the opposite of what the original sign was every single time. M stands for multiply, so you multiply the two terms together to get that A times B. P stands for plus sign, because that will always be a plus sign no matter what was in between the two terms in the original parentheses in the original problem. And then the last S is square, that's the B squared part. So SOMPs, maybe that's harder, I don't know. Square, do opposite sign, multiply the two together, do a plus sign, and then square that second term. All right, or you can just remember this little equation, whichever works best for you. You will have to factor perfect cubes, so however you do it is up to you. All right, so we're gonna do problem number 3 because that is factoring perfect cubes. All right, so here we go. Okay, now I know this is a perfect cube because 8 is a perfect cube. It's 2 times 2 times 2. And 27 is a perfect cube. It's 3 times 3 times 3. So I can factor this using that perfect cubes technique. All right, so to make my first parentheses, all I do is take the cube root of each term. All right, the cube root of 8x cubed is 2x. I keep my minus, it stays the same sign. All right, and then the cube root of 27 is 3. That's the first parentheses. You just cube root each piece, each term. Second parentheses, you can either have the formula memorized or remember SOMPs. All right, so you square the first part, so 2x squared is gonna give us 4x squared. You do the opposite sign, so since we had a minus to begin with, it's now gonna be a plus. You multiply the two terms together, so 2x times 3 is going to give me 6x. You do a plus sign always, and then you square the last term. 3 squared is 9. That is factoring perfect cubes. All right, now, just like the other ones, we want to go through and make sure we can't factor anything else. All right, so 2x minus 3, that's all the way factored. I can't do anything else with it. So then I look at 4x squared plus 6x plus 9. Guess what? That is also already factored. You can try factoring it, but guess what? Spoiler alert, it never factors more when you're doing perfect cubes. The first parentheses might factor more. The second one, however, will never factor more. All right, but it is only a quick check, right? You would need to do A times C, so 4 times 9, which is 36, and then B, which is 6. So you're looking for two numbers that multiply to 36, add to 6. Guess what? They don't exist. It doesn't factor. Okay, so that would mean this is now in fully factored form. All right, so now we have to do the second part of the problem, which says to find all of the zeros. All right, so we're gonna take each piece equal to 0, solve for x, blah, blah, blah. This one's easy, x equals 3/2. This one, not so easy, because guess what? Since that doesn't factor, that means I have to do quadratic formula. All right, let's do it. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Yes, I do Pop Goes the Weasel to quadratic formula, and it's late at night right now, so I did sing that for you, and I apologize if that hurt your ears. I'm not a good singer. That's okay though, it doesn't matter. No one's here to judge me. If you judge me later in the video, guess what? I'll never know. Okay, so that's our quadratic formula. Now we just get to go through and we get to simplify. So that's -6 plus or minus. I'm gonna use my calculator because I don't even want to try and do that by hand. So -6 or 6 squared times 4 times 4, 9, blah, blah, blah. Square root of -108, perfect. All over 2 times 4, which is 8. Now, yes, you must simplify. First off, -108, I'm going to go ahead and pull out that I. And guess what? 108 can be simplified even more. So yes, I do want you to simplify that. All right, 108, 36 goes evenly into 108. I'm pretty positive. 108 divided by 36, yep, it's 3. So I can rewrite this as -6 plus or minus I root 36 times 3 all over 2. And 36 is a perfect square, so that becomes -6 plus or minus, bloop, 6I root 3 all over 8. Why did that turn into a 2? Nobody told me. That's because I'm by myself. So who would tell me? I don't know. My brain. I don't do math at nighttime well. Okay, now we can do one more thing to simplify this problem just a little bit further. All right, because every single piece is divisible by 2, I can divide a 2 out of everything. This only works because all the pieces are divisible by 2. So I can divide 6 by 2. 6 divided by 2 is not 2. 6 divided by 2 is 3. 6 divided by 2 is 3. 8 divided by 2 is 4. All right, so I just divided everything out by 2. It's taking a sec. There it goes. We're all caught up now. So final answer here is x equals -3 plus or minus 3I root 3 all over 4. Oh, that was a big one. Quadratic formula. All right, so those are my zeros. And my original equation, I had 3. It was the exponent of 3, so I need to make sure I have all 3 of my zeros, and I do. That's 1 0, that's 2 zeros, that makes a total of 3. I found them all. Amazing. I'm done. Hopefully that turned out really good as a video. If it didn't, that's okay. You're gonna have to watch it anyways because I'm not redoing it. So that is it for today. Hope you liked this video. Hopefully it helped you figure out some new methods for factoring. If it didn't help you at all, that's on you. I tried my best. All right. Bye guys. I'll see you in the next one.